Hello and welcome to another video. In this video, we will see about the root locus technique used in control systems. The root locus is a graphical method to determine the characteristic equation as system parameters vary. So this method helps us to analyze the stability and the transient response in a system. Suppose we are giving some input to the system and we need to analyze the output of the system. When we are giving a step input to the system, the output response can be settling at the final value. It can have oscillation and then settle at the final value, or it can have continuous oscillations. So it can have any kind of these responses. So our aim is to analyze and predict the response of a system, so whether it is stable or unstable, and can the transient response be modified. So this part which varies is called the transient part, and this part is called the steady state. So root locus is a graphical technique which gives us information about the performance of the system. So earlier we have seen the response of a first order and a second order system. The real strength of the root locus lies in its ability to provide solutions for the system of the order higher than 2. So for a higher order system, how the system stability is analyzed. So root locus helps us to analyze the stability and the dynamic behavior of the higher order system. So it provides us an insight into how the poles move and affect the system. So graphically, we can visualize how the poles move and how the system stability is affected. The poles of the system are the roots of the denominator of the transfer function. Suppose you have a transfer function like this. The pole are the roots of the denominator. So here the pole is at -2. Now this pole will be affecting the stability of the system. We will see how we can visualize the stability of the system by analyzing the locations of the poles in the S domain. Now roots of the numerator of the transfer function are called the zeros. Here the zero is at equal to 0. Now the poles, the roots of the denominator, those determine the system stability and oscillations and responses. So how the transient responses is affected, how the oscillatory response, how the system responds to the input, all those are system behaviors, and those are characterized by the poles of the system. Suppose you have an open loop transfer function of the system k g of s, and you are adding a feedback h of s to make it as a closed loop system with input and here the right output. Now the closed loop transfer function of this system with the feedback transfer function as h of s would be k g of s divided by 1 plus k g of s, where r of s is the input, c of s is the output. Now the reduced system block, that is the equivalent transfer function of the system is k g of s divided by 1 plus k g of s h of s. After block reduction, you will get this equivalent transfer function. And the characteristic polynomial, which is nothing but the denominator of the equivalent transfer function. This characteristic polynomial is 1 plus k g of s h of s. So here we notice that the value of the poles of the transfer function changes with the value of k. So whenever we modify the value of k, the poles of the transfer function changes. Now a locus of the roots of the characteristic equation as a parameter of the system gain, as the system gain varies, is called the root locus. So as the name says, it is the path of the roots. Root locus. Locus is path. So the path of the roots are called root locus. So here we will change the value of k, and as the value of k changes, how the poles are changed. Poles of the closed loop transfer function. That is nothing but the roots of the characteristic point. So how the roots change, that is plotted, and that is the root locus. That helps us to analyze the stability of the system. And we will see the basic idea of a root locus with an example. Suppose you have an input r of s, output c of s, and the open loop transfer function as k divided by s into s plus 10, and we are giving a unity feedback and a negative feedback. So we can reduce this entire block by using the formula g of s by 1 plus g of s h of s. Will be k divided by s square plus 10s plus k. Now the characteristic polynomial is s square plus 10s plus k, which is nothing but the denominator of the closed loop transfer function. Now we are analyzing what happens when the value of k is changed. Suppose the value of k is at 0. Then the roots of this characteristic polynomial would have one location, one pole here, another pole here. So at k equal to 0, we have two poles at the location 0 and at minus 10. And as the value of k is increased, say k equal to 1, we will have one pole here, another pole here. Similarly, at k equal to 10, we have one pole here, another pole here. And at k equal to 25, we have two poles here at the location minus 5. So when k equal to 25, we will have two roots at the location minus 5. And we can increase the value of k again. And when the value of k is greater than 25, we have two poles, one moving up, another moving down. So as k is increased more and more, this moves away. We will try to plot the path of the k. So starting from k equal to 0, the path is like this, one pole moving like this, and it is going to infinity. Another pole moving from 0 and it is going to infinity. So from this graphical representation, we can have the following conclusions. When the value of k is less than 25, we have an overdamped system with poles on the real axis. And when the value of k equal to 25, we have critically damped system with the two poles at minus 5. And when the value of k is greater than 25, we have an underdamped system with poles having real and imaginary part. So out of the two poles, we cannot clearly say which pole goes up and which pole goes down. One of the pole moves up and one of the pole moves down. So this is the basic idea of root locus. So we will change the value of the gain and we will try to plot how the poles move. So the locus or the path of the roots we are trying to plot, and that is the root locus. So with basic idea, we will proceed to the properties of the root locus and rules of the root locus, how to plot the rules of the root locus. We will see that in the next videos. Thank you.